Thanks for joining us today. John and I are here from Beatport out in Denver. So that's Beatport, not Beatport. And here we are to talk about batch encoding audio workloads on Kubernetes. So we've had some interesting use cases this year. So my name is Leigh Capili. I'm an infrastructure engineer with Beatport. We're on the same team together. And you may have seen me around. I help participate with SIG cluster lifecycle, collaborating on projects such as KubeCon, trying to move the upstream of Kubernetes forward. Cool. There's my Twitter handle and stuff, and picture of my dog. Also, you guys totally missed out. I went to the parkour gym last night up in Redmond, and it was a good time. So.
Hi, I'm John Slivka. I'm also an infrastructure engineer at Beatport. I've worked for some much larger companies in the past, doing things in the observability space with open source tools. I've also worked as a software engineer for object storage as well. And my GitHub information is here as well, if you want to get in touch with me afterwards.
Also, a shout out to former Beatporters in the office. Thank you for coming. So, we replaced the stuff you built.
So quick show of hands, how many of you guys listen to electronic music? Okay, cool. And how many of you people still download your music and keep it on your computer? Yeah, okay. So that's pretty much our market. We're in a niche space nowadays with Spotify and SoundCloud and everybody else, but it's still a good market for us. And our customers are mostly DJs at this point. They still like to download their music and curate it themselves. So what is kind of the story about how we got here as it relates to DJs? We started out in a very physical medium of having analog signals on vinyl platters. DJing at that time was literally getting together and mixing these two records like this and queuing it up on the headphones, and that was a big deal. And then we finally got into the digital space with CDs. This was a little bit more of a compact format. We were able to carry things around a lot easier. You could fit more of these in record stores, but it was still physical. Finally, we got flash storage, and you saw things like the iPod and these digital download services like iTunes and Beatport, which actually came about around the same time.
And so this is where Beatport's main business is and has been for about the past decade. We've been incredibly successful, even every month still today. Our record sales in a digital format, they grow every month. And people love our product because we know our customer. DJs, they like having the asset, and not only that, but they need it to have the license in order to perform in the biggest clubs in the world and to be able to post-process their audio with their own tools. But as Beatport, in an industry that really hasn't pivoted or changed much, right? And now we've seen the likes of SoundCloud coming in, and there's a new format of DJing starting to happen with creative sharing of audio and mixing. Some of you maybe have been to Burning Man and know, there's a lot of creative sharing of audio happening there. How does Beatport take our legitimate business into the cloud? And what does it mean to use the cloud to provide new tools and new platforms, new products and new ways for people to more instantly and more accessibly DJ in creative manners with less of the arduous workflow of custom file naming and playlist curation and stuff, right? How do we make the experience more like this century? And that's the question that we asked ourselves, and that delivered some interesting business goals, some interesting business problems. We decided on a couple of product directions, some really exciting stuff coming down the pipeline for DJs. It's really the next pivot in the format of how we perform and play music. But we have 8.5 million tracks in our catalog right now. And these new products require all of our raw assets to be encoded in creative ways that can be served in that instantaneous format. And we're not going to do that, with our petabyte storage cluster in our data center. We need to be able to do that at low latency all around the world. And so the business goal here that we're talking about, what we've completed and delivered on, was recalculating the BPM and doing key analysis on our entire catalog. And then during that process, also taking the raw PCM frames from our waves in our petabyte storage cluster in the data center and replicating that not only in our bare metal location, but also into Google Cloud in 128 kilobits per second with this AAC encoded format with more formats to come. And this system that we designed needed to be maintainable and pluggable in a way that was going to be easy to maintain regardless of who was operating on the system.
So we're going to be overloading a couple terms here, so I just want to make sure that everybody is using the same language. So I've outlined some definitions here. One is master. When we talk about masters, we're typically talking about our authoritative copy of the PCM data, the raw audio data. A derivative asset for our purposes is going to be anything that we derive from that master. The back catalog is basically the entire of our collection, that petabyte of storage that Leigh's talking about. We track all of our releases. Our releases are a collection of all the tracks that we have in our catalog. So these are just logical groupings of those things. And we're probably going to mess this up. We do it all the time, but for our purposes, a task is any set of work that we put into a pod. We'll probably end up using the term job at some point as well. We'll try to differentiate from Kubernetes jobs from tasks here. So some of our constraints here, we couldn't immediately migrate all of this work. We had a lot of dependencies. We have a data center that we've been using for a very long time. A lot of our assets were still in this data center. So we needed to design a system that was portable, that we could kind of prototype out in the cloud, which we ended up doing, but ultimately run that first iteration in our data center in a cost-effective way, and then be able to later port that out to the cloud without any additional work being done. So some of our other constraints were supporting these multiple modes of storage. We have some Google Cloud storage that we've been using more recently. We still have a giant NFS cluster that's hosting most of our assets. So we need to be mindful of these two different read and write modes going between locations. We wanted to minimize our round trips across the network from the data center to our points of presence in Google Cloud. And we needed to make sure this system was observable. This is not as well documented or written about kind of how you observe ephemeral workloads and keep track of those and be able to see things like failures and successes and make sure that your system's correct and it's doing what you want it to do. Mm-hmm. We want to be able to look at concurrency, see how many of these jobs we can complete in a given period of time and minimize those errors.
Mm-hmm. So with this term that we kind of pointed out, which is what is a task, we have some business logic, right? The first thing we need to do is we have to authenticate with our systems, because if there isn't the ability to have an authentication token with, say, the Beatport API, it's not really a good point in doing much work. But say you're authenticated. Now you've got to fetch the asset, right? Fetch the master from wherever storage backend you've currently plugged in to the workload. And then once you have the asset in some kind of local storage, you can then run all of our vendor binaries, some of those being from third-party companies that we're partnered with in the industry for the improvements in VPN detection and key detection. And then also, like minting waveforms so that you can visually interact with the track. It's very important for a DJ to be able to identify where the drop is in a track, say, right, like that. And then also, like, say, FFmpeg. This is an open source component that we're able to take advantage of to do correct transformations of PCM data into the encoded formats that we need, such as AAC. And so you can see right here that we have like a very simple DAG. It's a directed graph. And there's some serial components at the beginning of the business logic, and then a fan out into components that are no longer dependent on each other at all. And this can be represented very easily as a single unit of compute as a pod. And so the pod representation of this business logic, it doesn't change really much at all. But you can see there that we have these additional volume mounts. And it's important, if you've never worked with init containers before, to make note that the list of init containers in a pod actually runs in serial. And this is something that you can do to keep your workloads consistent. You can say, hey, like, run an authentication pod first, and then take that, mutate something in a volume, and then run another container on the contents of that volume, right, to maybe fetch the authentication token for like getting something out of storage. Here you can also see that the read-only masters are only accessible to the init containers and the necessary ones for pulling that asset. and that none of our vendor binaries actually have read access to our entire catalog, which is a very important security, like it's a least privileged model, and the pods API allows us to implement that. Same thing, the waveform container in the containers array, when it's running alongside with all of its friends, the mount namespace inside of that container is different than the mount namespace of the MP3 encoding container and the AAC encoding container. It's a least privileged volume mount model. Same thing with, if you wanted to use Google service accounts in order to enforce privileges with the with the Google storage buckets. And so we have those things swappable with the feature flag and some pod features. So now that we kind of know how to actually represent the compute in a pod, then the question becomes, how do you run 8.5 million of these over a long period of time in your cluster?
Yeah, so all of this stuff is very simple. We're using well-tested software. We're not going out of our way to write really complicated distributed systems in code. We have stuff that works, right? These are things that we could run on our laptop. We just want to be able to do it at scale and utilize our entire data center and use that compute without writing a ton of code that we have to test, right? We have a business goal that we need to deliver on and not a lot of time. So what we decided to do is introduce a queue into our system for publishing these jobs. This is kind of important because we didn't want to rely entirely on the Kubernetes API to store this state, right? We don't want to have a single point of failure and lose 8.5 million jobs that we need to go and query our database for again. So that was a conscious decision that we made. So then the question we have to ask ourselves is, how are we going to take a simple message, right? What is the asset we're working with? What do we want to derive from that asset? And how can we get that into a language that Kubernetes understands and allow Kubernetes to handle the scheduling of those workloads? So we came up with this thing that we wrote, which is a Python Kubernetes client that is running as a daemon. It's reading off this queue. It's able to interpret the intent of those messages and publish Kubernetes job objects to the API.
Yeah, that's this section here.
And then ultimately, these end up as pods that get scheduled in our data center on non-homogeneous nodes. You can also see here we're communicating with an external API that's storing some of the metadata that we compute. We do things like checksums and metadata, the BPM and key that Leigh was talking about. So what do these messages look like? What is the minimum amount of information we need to give our system to get it to do work? So we have a request ID up here as well, which is for tracing. And then we have our release ID, which is our collection of tracks that this specific asset might be associated with. We have an asset ID, which we use to communicate the unique identifier to the API. We have an asset GUID, which we actually use in our storage layout. So this is important as well. And then give me a list of things I need to produce. What are the different types of derivative assets that we want to be able to plug into this system?
And so we kind of settled, okay, this seems like a pretty decent way to move forward, right? This was all just architecture and talk and whiteboarding at that time. And then we, decided this seems like it's a pretty decent thing to try and prototype, right? We need to build a system that actually exhibits some of this behavior in order to determine whether or not this is going to work as a production system. Because we started looking around, got on Google, started reading blog posts, and it doesn't really seem like many people are at least writing about how they manage batch workloads on Kubernetes. And this wasn't something that we really knew was going to work. And we've got the architecture basically where you submit a bunch of messages to the queue, and then the dispatcher mints those messages into compute that's specified in Kubernetes. Kubernetes does the rest. Right. Now, these were our hardware assets. It's like we've got basically one rack of servers in our data center. They're from 2012, 2006. Shout out to the Dell PE2950s. Those things are tanks. And if you've ever racked hardware, you can understand why we might just have a bunch of old servers hanging around. It's because these things were decommissioned from production for good reasons, like bad RAM slots, failing DRACs, spooky stuff. It didn't run our workload properly, you know. It's just like things that you don't really want to run in production. And we thought, well, could we cluster these into like a Kubernetes cluster? I mean, like these things do not have, you know, like any business running Kubernetes. We decided to install CentOS on all of these things and start installing Kubernetes. This is a big deal. You see, this is a bare metal installation that requires network topology updates, actually like sending people to the data center to like cut cables, plug in NICs, rack things, replace RAM slots. This is a serious undertaking. And like when we decided to prototype the system, when we had targeted running this workload, this cluster didn't exist. But if you remember from our business constraints, we wanted to build on Kubernetes so that we would have portability. And the cool thing is that we could go straight to GKE and we could say, hey, like, can I please have a 13-node cluster? Like, can I please start developing my software? Like, can I see if this is going to be a reasonable way to achieve our business goal? And John and I alone were able to, in a week, provision the infrastructure, provision the HA RabbitMQ cluster using Helm, and write a simple Python program to start consuming the messages and start minting things into the Kubernetes API. And we were able to model that the workload was actually going to schedule and meet our performance needs. And this was a week. One word of warning is that I would highly recommend that if you are going to consume the Kubernetes API with software, please use a typed language such as TypeScript or Golang or like something sane. Because using the Python Kubernetes client was easy to iterate with because you didn't have to compile anything, but like type mismatch errors such as accidentally swapping volume for volume mount, like those would sometimes submit to the API as valid API objects, and then sometimes the program would blow up and the error messages are like walls of JSON. I would not recommend writing in Python. And we're actually going to demo a subset of our business logic right now with basically a system on GKE. So I can kind of show you how it works a little bit. Here we have a storage bucket. It is just a bunch of test media. We have folders with a bunch of WAV files. This is raw PCM data. We've got an empty storage bucket called BP KubeCon demo MP4s. And then here, using this is Henning Jacob. He's currently at Zalando, I believe, a great contributor in the community. He built this front end that basically shows you all of your nodes in the Kubernetes cluster. So all these purple boxes are nodes in a GKE cluster that we provisioned specifically for this purpose. And all the little green boxes that are currently highlighted are like things in kube system that are being managed for the Kubernetes cluster, such as Calico pods and things like that. So if I start like filtering for things, you can actually say, hey, like, where's the dispatcher? And there's a little green pod that says, yep, that's a dispatcher. If I want to say, hey, where's my RabbitMQ cluster? You can see that there's 3 pods distributed in an HA configuration across the cluster. So this is kind of showing things. It's called KubeOpsView, and you can install it with Helm into your cluster really easily. Yeah. So if I filter for encode jobs, and then I say, hey, in our namespace, get me the list of pods. I'm just going to get a shell right now in this pod. Normally we do this from just like a laptop or a management machine. But what I'm going to do right now is I'm going to use a script and a CSV file to just submit a couple of messages to the queue. And once those messages are on the queue, the dispatcher, our little Python program that's currently running right there on the pods list, is going to see those messages on the queue, and it's going to template a bunch of compute for the Kubernetes API. So here's the CSV file. It's got 201 tracks in it, each with a unique GUID. And then if I run publish on that GUIDs file, demo, you can see we submitted 200 messages to the queue here. It's just a bunch of info. And very shortly, as long as my kubectl proxy is still up, yeah, you're starting to see a bunch of very like matrixy style pods starting to pop into the cluster, right? Now, the UI isn't really built for this kind of like queuing use case, because right now there's a bunch of pending pods in the cluster, and so it's actually kind of funny, like they just start to get in line over here, and they're not currently scheduled any nodes. That's kind of cute, right? But so right now, we've got a bunch of Kubernetes pods in the cluster. Well, let's go ahead and describe what our workload looks like. Check it out, all right? Bunch of components. Oops. All right, so we have, this is not precise, about 126 of those things running right now. And let's like maybe describe the pods. Cool, so here we can see, oh, okay, in this container, we've got a couple of volume mounts. It's got some secrets. And then here's like a shell script, you know, because like we write bash since we're infrastructure engineers. So here you can see it's like running ffmpeg and like stat, you know, it's getting like digests and putting things into a Google bucket with gsutil. But if you look at the mounts, it just has a local mount. Well, that's because this container up here, which is called fetch asset, has a mount, or actually this just has a secret that allows it to copy things from a Google bucket and actually populate the local storage bit, right? So that's kind of how the compute workload is structured. And if you see that these pods in purple, they're actually workloads that have completed computing their assets. And so if I go to my previously empty Google bucket, I should now have tracks. I've got some folders. This is why we did the sound check earlier. Let's make sure that we can actually play a song. I hear that this is like from Finland. It's a new song that's just dropped. So hot right now. I think this is like a, do you know who this artist is? I'm not sure. He's really up and coming and everything. And it was like, yeah, it was like, yeah. Oh wow, yeah, those are good synths. That's solid. Let's turn it up, yeah. Yeah. You can see, like, we really know our customers. This is something I'd play in the club tomorrow. Oh yeah, good stuff. Yeah.
Yeah.
Yeah. We'll have to look up that track name later. All right. Anyway, it works. So that's our demo there. Thanks, Kubernetes. So you know, things go beyond prototype quickly.
Yeah. So there's a lot of things that we need to look at when we're designing this system that you might not immediately think about in other contexts. Our previous system was long-running daemons that were listening off of a queue. They're each responsible for a specific task and like compressing audio or calculating BPM. So we were fetching the asset multiple times based on the job that was being performed. This is a lot different, this approach, right? So we need to keep track of our pod failure rate, how many of those are succeeding, how many completions we have per minute, concurrency. Garbage collection was a big one. I know there's some efforts being made there now, but what we ended up doing was writing a cron job to basically pull for completed pods and then delete them. And then we need to re-queue and record failed jobs. We need to know what went wrong with the system and how to diagnose it.
Mm-hmm. So this is an example of a graph that we have in Grafana. We decided to install the CoopPrometheus stack. This was actually kind of to monitor some of our other workloads in Kubernetes. CoopPrometheus is a solution from the CoreOS team originally designed to help service their Tectonic Kubernetes platform as a service product. And CoopPrometheus comes with several things right out of the box. You can install it as a Helm chart from their Git repository, and it's got kube state metrics, which is an exporter that's designed to basically constantly pull the Kubernetes API with the shared informer and then expose things that are natively about the Kubernetes API as metrics to Prometheus. Prometheus in CoopPrometheus is actually operated by Kubernetes operator. We also get node exporter that's scheduled as a daemon set across the entire cluster so that we can get native metrics about the Linux machines that are running our cluster. And then on top of just having Prometheus operator with Prometheus, which is the data and query engine, we also have Grafana to then have our persistent dashboards so that we can actually put things together for a constant monitoring view of our cluster. And here on this dashboard, we have encode pod phase counts. Right, so pods in a specific phase such as pending, or running, or completed, or failed, or unknown. Luckily, there's none that are unknown on this graph. And what you can see happening here is that purple is the line that represents the total number of pods in our cluster. You can see that's kind of like spiking up like every couple of seconds. And that's because the dispatcher, the little Python program that we wrote to watch the queue, it's trying to keep 1,000 pods in the cluster at any one time. This is kind of a number that we just picked for back pressure. You'll know that if you've ever written a queuing system that you need to write back pressure algorithms, right? Or some kind of back pressure threshold. And so we're using the number of pods that are currently in the API as a limiter on how many things we should pop off of the queue at any one moment. We have the cron jobs in the cluster to clean up things such as completions and failures. And then you see this yellow line of pending pods. Right? So when we immediately submit things to the cluster, they're immediately going to be pending. But as they start to get scheduled, and as they go into their container creation stage, making sure that the Docker images are pulled down at the proper image tags, then we're going to have running pods. You actually see right here, I'll point on my mouse. Right there's this little blue line. That says that there's about 90 running pods in the cluster at any one time. This was 10 nodes in our data center. And then we see our completion rate kind of spiking every now and then. Right? Now, this red bit right here, at this time, this was an early snapshot. This is the important bit about having persistent metrics across your cluster at any one time. We have metrics from back when we had a failure of our API, which is an external system to this batch encoding workload. And at this time, we were dealing with lots of different failures, and so we wanted the failures to stop the system, which meant that our resubmit cron job was disabled. And we had our failures spike up, hit the total pods threshold, and the dispatcher stopped submitting things to the cluster. At this point, I responded to the incident and basically just ripped off all of those jobs and put them back in the queue after I fixed the API. So this workload kind of monitoring, we wrote this query on Kubernetes metrics, not anything specific to our system or anything that we had instrumented. We're just running shell scripts in pods. And it was really cool to be able to just install CoopPrometheus and then suddenly get this kind of workload visibility in the way that we were like running things. It's an advantage of using the Kubernetes API. This one's a really funny graph as well. This is system utilization. So this is something we really struggled with. Even though our system was fast, it didn't seem to always be saturating our nodes. For quite a while, we were running at 100 cores, and I decided to basically stop the dispatcher, which is to basically stop submitting things into the cluster, letting the queue just stay persistent. And I modified the dispatcher to basically ignore resource requirements. So to submit compute workloads to Kubernetes that didn't actually ask for like 2 CPUs, right? Or limit them at 5 CPUs and a gig of memory. And then this happened. And we don't know why this was. This was a good thing. We had a hypothesis that maybe that there was some temporal slicing from the way that the C groups were getting put together. We thought maybe let's just remove the resource requirements. I was actually talking with the Zalando folks, and they found that sometimes this helps with saturation. And we jump up immediately to like 350 CPUs, which we're like, oh yeah, this is awesome. Like it's going to go 3 times faster. And that's not what happened. It didn't improve our throughput at all. So we don't really know what happened, but it was using a lot more CPU, and we reverted that change. You've got to like apparently know these things about requests and limits, but I have so many questions. If you read the Kubernetes documentation about resource requirements, this is a huge area where we can improve, because it's not incredibly clear when you're reading the documentation. There seems to be this conflation of pods and containers. Like that multiple, a pod can have multiple containers inside of it, but then it'll be talking about a container C group and then swap to using pods. And there may be some semantic errors in this documentation. It's really difficult to understand how things are structured. And like say if I provide one container that has resource requirements and then provide another container that doesn't, like what happens to the pod C group? And how do those C groups get shared across multiple CPUs if the pod C group is then bigger than a single container? Or sorry, bigger than a single CPU. The Canonical folks have this HackerNoon article called Job Concurrency in Kubernetes. with LXD and CPU pinning to the rescue. Actually really interesting. I recommend reading it if this whole resource requirements C group mapping conversation is piquing your interest, because there's some nuances here with like even the CRI runtime you pick. Like what's the Docker default of like asking for 1100 millicores? The answer to that question is not simple. And they also cite this guy, ST Graber, who seems to be from the LXD project, probably one of their peers, who has more detail about how LXD kind of handles these things. And they actually suggest that for a workload similar to ours, they were benchmarking video encoding, was that the best way to get throughput in the system was to run several LXD Kubernetes workers on a single bare metal node. So to run a Kubernetes worker in an LXD container, right? And then to have that LXD container run the kubelet inside multiple times per bare metal node so that the CPUs would be pinned precisely to the hardware underlying the actual compute. And yeah, this was something that was not very simple. Luckily, we were able to scream past our business requirements anyway. We also ran into other Kubernetes specific issues as well as several workload issues that we dealt with internally. But these are probably the more public ones that we definitely wanted to take a note of in this talk. So when we first built the system, everything was fine and peachy and happy and the prototype worked. But then, as we started to load test the system, say, put 10,000 jobs through the cluster or 100,000 tasks through the cluster, that all of a sudden we'd be looking at our metrics and there would be gaps. And you wouldn't really know why. It was really hard to correlate what was happening. And then we looked at the pods in the monitoring namespace. And we saw that the kube state metrics pods on the single kube state metric pod in the cluster was in a crash loop. Well, when you deploy kube state metrics, it has a sidecar inside of it that comes from the Kubernetes autoscaler repository. It's called the add-on resizer, or pod Nanny. Some of you may have interacted with this component before. The pod Nanny's job is to take a per node resource requirement, look at the number of nodes in the cluster at any one time, and basically if the number of nodes in the cluster changes, it will multiply that resource requirement and basically rewrite its pod definition. So it'll grant itself more resources in the Kubernetes API as the cluster grows and shrinks, which is a really interesting way to run a workload. Unfortunately, the per node resource requirements are kind of conservatively tuned to normal usage of Kubernetes. And when you start putting as many objects as we were putting in the API, we were just totally blowing this per node number out of proportion. We had to scale the kube state metrics per node resource requirement using the Helm values to probably about 20 times the size it was in order to handle the number of objects we were putting into the cluster. And that fixed our ability to view the needed metrics to observe the system. So the solution was to just scale the KSM Helm values. This one is more interesting because the Kube Controller Manager is a core Kubernetes component. And so Kube Controller Manager, we're seeing basically right now that it times out on the metrics endpoint in Prometheus. This is an interesting one, if there are any contributors in the room, we need to open an issue for this, or I'm not sure if it's been fixed. We're running Kube 1.11, and we've just recently released 1.13. But basically, it seems to track metrics for every single object in the cluster, and we're not really sure. It's unclear if there's a garbage collection or time period for this, because we blow the number out of proportion. And it takes 4 minutes to return this metrics list after running our workload for about 3 hours. And basically the result is that the Prometheus scraper setup is timing out. And the only workaround that we kind of have right now is to restart the Kube Controller Manager. This is a safe operation to perform. You can just go delete the Docker container backing the static pod on the control plane. So I guess you could put that in a cron job. But we should fix this. It should be trivial. I'm not sure if it's fixed in more recent versions of Kubernetes or not.
Yeah, so you might have noticed in Leigh's demo there wasn't really any talk or kind of demonstration of jobs. There's a reason for that. We ran into some issues early on. kind of past our point where we were like, oh, okay, let's shoot like 10,000 messages and create that many jobs. We weren't seeing issues. The first time we started kind of a sustained load test of our system to kind of, like do a pre-trial of this long, 3 months of encoding we had to do, we started running into issues with jobs over time. We started to see list operations and delete operations, things we needed to do for basic garbage collection. They were starting to degrade the more objects we were adding into the Kubernetes API. And since we were using this back pressure mechanism, we were essentially kind of piling up these issues over time, and the system would just stop completely. And then we couldn't even go in and use kubectl delete or anything like that to get the system back to a healthy state and allow this workload to keep going. So we think it might have to do with the job controller and how it waits for its children pods to get cleaned up. There might be some additional logic that has to be done there. We weren't sure. And we still don't quite know yet. We're still sort of figuring it out. There's a lot of variables. We kind of had, like I said, we had a business problem to solve and not a lot of time. So we decided not to dive into Kubernetes internals here and just go ahead and use regular old bare Kubernetes pods. So what are we losing out on if we don't use jobs, right? These are sort of the basic features of jobs. We have parallelism. We have retries. We can do things over again should they fail. And we have completions, right? We don't really see a need to complete the same job multiple times. We get retries because we have this queuing system and we have an operator that will go in and grab those failed jobs and put them into a dead letter queue. So we didn't need to worry about that. And parallelism was just not something we needed for this encoding project. And I'll also point out that there's garbage collection, I think automatic garbage collection as of 1.12 alpha. But like I said, we were running 1.11 at this point still. So yeah, this is how we're cleaning things up at the moment. We just have a cron job that checks for successful pods, and we'll just go ahead and delete those. And then we will dead letter our failed stuff so we can add more work to our system. So yeah, like I said, we're not keeping state in Kubernetes. We're just going to use Rabbit to store all of that work that we need to do. This has kept us out of trouble so far. And a lot of this stuff I've touched on. We have a maximum number of pods in the API, and we have some pretty good performance at this point that we can live with.
We ran into some other interesting things. When we started to use the system, this was actually independent of any Kubernetes-centric API. Once we had like thousands of things in the API at any one moment in time, we actually had a kubectl formatter issue that was plaguing us. The default formatter would panic past like 900 objects, but somebody fixed it because now if you use a newer version of kubectl, it doesn't happen. That was frustrating though, because then you had to like pass your own formatter flags in order to get it to work, and it probably cost us like 4 hours of our lives. We also noticed some things about the API quality of batch v1 jobs versus core pods. Obviously, pods is like the basic unit of Kubernetes. Like, it's one of the most well-tested, well-exercised, most written about, like best documented, regression-tested, performance scale-tested API that we have in the code base. And it's a big code base. But when you look at like the usage of batch v1 jobs, it's really difficult to find people who have written about actually deploying that, like a system to production on the batch API, like outside of just little tiny workloads like, oh, run a cron job here, or run some jobs as part of a Helm test pipeline or something like that. And we found that field selectors, it's not like a very public or documented thing, that some of the fields in the jobs API actually have typos in them. And there's not as many of the field selectors in the jobs API as there are on pods. And that makes things really useful if you want to, like, say, put together a runbook on like just using kubectl to respond to a system incident. I actually have an example of something that we did with the pods API. Here's our internal runbook for the system. We wrote a JQ program on the kubectl JSON output. And so you can like basically parse init container statuses and container statuses, and then get the exit codes. and put it out in a nice table for every single pod in your cluster. This is a truncated version of the output that says, oh, you know, like you had some errors in your run of a million things. Here's like some audio AAC failures. Here's some BP API auth failures. These pods are still in the cluster. Like, go look at it and fix your stuff. And so switching to that API bought us some wins and started some interesting conversations in SIG API machinery. So thank you especially to Jordan Lidgett. Clearly, you know, the performance of the pods API, it's designed to scale to like 30,000 nodes. So it passes our needs for completing a couple of million executions. But we found that with the batch deletes, we were not able to keep a production system running with jobs. And so we had to give up the retries, as Slivka said. The end result was that we were actually able to complete the encoding of our entire catalog of 8.5 million tracks in about 80 days. And that was 63 days of runtime of the system on the storage backend. There were some storage incidents and API issues and some deployment things where we had to basically stop the workload in the cluster to free things up. And because that was done in a Kubernetes native way, like we could use the cluster to kind of perform other tasks. And this was a pretty successful project for our company. So I know that when we wrote this talk submission and when we submitted it, we hadn't actually built the system yet or operated the system in production, right? Like we were just in the middle of load testing. And the title of the talk was Encoding 250,000 songs a day with batch V1 jobs. And what we were able to actually deliver after our estimations and running through all the problems that we kind of told you about, as well as some others, was encoding 140,000 songs a day with core V1 pods. And this was a really successful project for us. Thanks for coming to listen to our story. Yeah. These are our Twitter handles. You can reach out to us, and we're absolutely open for questions if we have a mic to go around at all. No?
We can repeat the question.
Yeah?
It's fine. Yeah.
Hey, what's your question?
So why use RabbitMQ, especially when you have global PubSub? And then building on that, why not use Google Functions, which actually integrates with PubSub and can read right off the queue?
That's a really good way to do that. So the question is, why use RabbitMQ in your data center? And why not use Google Cloud Functions to perform the compute workloads? And this has to go back to a little bit of our business constraints. So the first thing is cost effectiveness and the reuse of our data center hardware. The answer to the RabbitMQ question is that we already use RabbitMQ for some other things and we know how to operate it. But you could plug the dispatcher onto PubSub, probably with some very simple Python client changes. Mm-hmm. And then as far as using the compute, I really love to do serverless. I think there's that news company out in Britain who uses a serverless pipeline along with like sharding out some video files, and they're able to like convert gigabytes of data in like half a second. That's a really, really fantastic capability. The cool thing about this system is that it is built on Kubernetes. Like you could run it on, say, a serverless Kubernetes platform, such as Azure, with their virtual kubelet. But yeah, we basically wanted to use a compute API that could be run inside of our data center. Serverless would be a great way to do this. We couldn't just move a petabyte of our storage out of our data center like quickly, though. So,
yeah.
Yeah.
Yep. Mm-hmm. So the question is, since you run a lot of short-term jobs, did you learn anything about operating DNS in Kubernetes? We run core DNS in our cluster, which is GA as of 1.11. Our cluster is installed on bare metal as a single node control plane with kubeadm. And DNS has been relatively boring. We do have our core DNS also advertising to our internal VPN, and we have like routable service IPs. So that was done with a couple of core DNS plugin modifications, but we didn't run into any performance issues.
And the number of DNS clusters or DNS queries internal to the cluster is relatively minimal because the API that it's talking to is run in a GKE cluster external to the workload. Does that answer your question? Cool. Hey.
What was the average runtime of these encoding jobs?
We just did some stats on this. Did you want to?
Yeah, it kind of varies wildly. We have some tracks that are like 2 minutes long. We also still host like 60-minute extended mixes. So it can go anywhere from like 2 to 3 seconds to like 30 plus minutes.
Sometimes like an hour.
For those really long extended mixes.
Yeah.
So I mean, we haven't done analysis and like removed outliers to figure that out, but I would say the average track, like what we expect is like a 5-6 minute track that takes about 6 or 7 seconds with a single core.
Yeah, and the question was what was the average runtime of the workload?
Yeah.
Also, we did take this into account because we were worried our dispatcher like does batches of submissions to Kubernetes. And we were worried about like a stampeding herd kind of problem. But because our songs on average are so varied in length, it kind of tends to randomize out and the workload becomes relatively stable after about an hour. So yeah, good question. Does that answer everything you were looking for? Cool, yeah. Hey, what's your question?
So in your dispatcher spec or whatever, you're able to say like, these are the 3 types of processes I need to run, like AAC encoding and some other encoding, waveform or something. Were you able to somehow make that change the pod spec itself so that you only pull those containers that you need to run those jobs? And not,
Yes, that's exactly what we're doing.
Exactly.
Yeah, so the question is, with your RPC spec, where you have a list of assets to produce, can you dynamically change the workload in the dispatcher so that it doesn't include all of the unnecessary containers? And that's exactly how we built it. So the dispatcher will only mint a pod spec based off of what the RPC actually specifies. Yes, yeah, the dispatcher generates the pod spec with the Python Kubernetes client. It's not from like a YAML file or something like that. It is not.
No. Another thing to point out too is we also map all of our different types of encoding or derivative assets to single purpose-built containers. So we have a Docker registry, and even for things like FFmpeg, we don't kitchen sink stuff. So if you want to encode like AAC files, we have a very special compiled binary for FFmpeg that only does AAC.
The asset, so that's part of the round trip, the network consideration, is like not pulling files over the network more than once. And a single pod is working on an asset and produces basically everything that you need for that asset at one time. And we didn't find the need to do any caching beyond that because you're already preventing like 7 or 8 pulls of the audio file for different things. Oh, yeah, that's already cached on the, that's handled by Docker.
Right. I think we do if not present, especially
if not present is the good one to use, yeah. So the question about that was what settings are you using for Docker image pulls in your pod specs? And if not present, we'll basically reuse the image. It's important to tag your images properly so that you don't bust that cache. Yeah, good question. Cool. Anything else? Oh, Tavis, did you want to ask something? No? Cool.
Thank you.
Well, we're around, so come chat with us. And if you have any more specific questions about your business problems, we'd love to kind of chat about batch encoding on Kubernetes. Thank you.